Good afternoon. It is late again. I apologize. I will have Monday's video done for you and ready for Monday morning, and it will be scheduled to pop on when you get into school. So the bell ringer today, we're going to talk about histograms, which was a lesson we finished yesterday. Well, actually today. I'm videotaping this on Friday. It's the middle of my tennis conference here in Austin, Texas, and I'm taking a break to make this video. Anyway, let's analyze the histogram below and let's describe it. What is the mean of the data? And is it symmetrical or is it skewed? First of all, what does mean mean? The word mean means average, okay? And the average would be something we would have to calculate. You would have to take every one of these columns and find out how many of each in this column there is and multiply the number or the frequency by the bytes per article. And that would find the sum of that and divide by the total number of units there are. That's kind of difficult to do. So we can actually sit here and look. There's a lot of values here, but if you look, if we were to try to find a balancing point, it would be somewhere right around here between 1,500 and 2,500, because there's a whole lot of values right here, but then there's a whole lot of values right here, and they're about equal in size. And as far as being symmetrical, remember when we say symmetry, symmetry means that both sides look alike, and obviously this is not symmetrical by any means at all. This line has a whole bunch of skewing to this side. It is skewed far to the right, and that's exactly how it's described. It's based on univariate data. Now, I forgot to mention this. It's univariate data, and how do we know? If it says frequency or quantity in the Y column, we can almost guarantee that we're talking about univariate data. There's only one value we're talking about, and that's the bytes per article. So we're looking at the different sizes of bytes per article for every article that they're describing. And those that have between 500 and 1,000 bytes, they number in a frequency of 3,000, and so on. The number of articles that have bytes between 1,000 and 1,500, they number anywhere right around 6,300. That's how many there are of them, okay? So it is not symmetrical, and that is skewed right. Fewer data points on the right of the histogram. You see that? So anyway, let's talk about good things. Found a pair of court shoes really cheap, and that's one of the reasons why I like coming to the conference, and didn't break the bank with it, so I'm really happy. Anyway, that's my good thing. Once again, if you get the opportunity to send me an email and share your good things with me, I would love to share with your classmates about the things that are good happening in your life. All right, let's go on to the lesson. So today's lesson is it's the 6th lesson in the unit on statistical studies, unit 3. It's called Analyzing Graphical Displays, and we're going to look at different types of graphical displays. We looked at one specifically yesterday, histograms, which is generally used to describe univariate data. This couple others we're going to look at describe several others, and we may actually do a little a lab in the class looking at different types of graphical displays. So let's look at this table we have here. We have a table of points per game for the Phoenix Mercury Women's National Basketball Association team back in 2008. They had 14 players in the roster for that season, and the players and their average points per game are shown in this table below. Okay, and you can see where the source comes from right there. All right, the smallest value listed in a data set is called the minimum. Now, most of you know what that means, but I write this down so that you can actually look at it and write it down in your notes so that you can have it for the test. Remember, we have cheat sheets for the test. The minimum of this data value set is what, and which player has the minimum value. So if we look, these are all in sequential order from the one with the most points per game to the ones with the least. So the player with the least amount of points per game is Jennifer Drabjanek. I can't say her name. And that is the answer to this question. At 0.8 points per game. Jennifer Drabjanek. Now, the largest value listed in the data set is called the maximum. Obviously, we said they were in sequential order, so Diana Taurasi has the maximum value, and that's 24.1 points per game. Now, the middle value listed in a data set is called the median. The median of this data set is what and which player has that value. Now look at the note. This is very important to understand. We're talking about a data set. If we have an even number of values, there is no middle number. If there's no middle number, because you have an even number of data points, you must average the two middle values to calculate the median. Now, if you notice in this case, there are 14 numbers. So we have to look at the 7th and 8th value. Latoya Pringle and Brooke Smith will add them together, which gives us an 8.5, and we divide that in half, and we get 4.25. And as I said, 4.25 is the points per game. The median is not a player. It's the average of those two players, Latoya Pringle and Brooke Smith. All right, now let's list the data set horizontally from smallest to largest, and we're going to write the median in the list in the appropriate location. We'll circle the minimum, the median, and the maximum. Okay, so these are all the value points we have listed in order from smallest or minimum to largest or maximum. Now we're going to put the mean or the median, in the middle. Well, we'll list the minimum, which is right here. Then we'll list the maximum, which we know. We'll put the median in there, which we calculated. Now, note that the median was calculated by taking the average of the two middle values. I had to point this out again because I want to make sure you understand how it was calculated. All right, now let's cover up the right side of the list in the new table so that you can only see 7 values below the median, 4.25. Find the median of these 7 numbers and circle it, and under that, write Q1. So 1, 2, 3, 4, 5, 6, 7. That middle value is this 2.4. We're not talking about these values over here, just the values on this side of 4.25. 1, 2, 3, 4, 5, 6, 7. Guess what? That value 2.4 is your Q1. We'll tell you what Q1 stands for here in a minute. All right, now we're going to cover up this left side, and we'll do the same thing with the right side. These 7 values has a middle number, and that's 10.1. We'll write that as Q3. Now, these numbers here above are called the 5-number summary. And they're separate. These numbers separate your data into the 4 quartiles or 25% sections. So in other words, in between the minimum and Q1 is 25% of the values, okay? And in between Q1 and the median is 25% of the values. And in between the median and Q3 is 25% of the values. And in between Q3 and a maximum is 25% of the values. And Q obviously stands for quartile. So Q1 is the quartile 1 number. That's the number that separates quartile 1 from quartile 2. And then Q3, that stands for quartile 3. That separates quartile 3 from quartile 4. All right, so let's look at what we can say about this. The data between the minimum and Q1 are the first quartile. That's here. The data between Q1 and the median is the second quartile. Quartile meaning a fourth of the whole. Data between median and Q3 is the third quartile, and the data between Q3 and the fourth quartile, or the maximum is the fourth quartile. The 5-number summary allows you to make a graphical display called a box plot or a box and whisker plot. The reason for this interesting name becomes obvious as you construct the graph. First, you need to decide on a scale. What would be a good scale for these data to count by 1s, 10s, or 100s? So let's look. We have a minimum of 0.8 and a maximum of 24.1. And there's usually between 1.5 points between values. Over here, you've got a little larger spread. There's a whole 10 points here. I would venture to say that 2 is probably a good number. Any of these work, but I think we're going to go with 2. So we're going to construct a box and whisker plot and follow the steps provided for this reference. Number 1, plot your scale. Number 2, place an appropriate label below the line. Number 3, place dots for your 5-number summary values about an inch above the line. And step 4, put a small vertical line about the size of this L on each dot. And use these lines to construct a box and whiskers. So here is your scale, okay? And we're going to put a label above or below each line. There's a line for the first one, 0.8. And here's one for the maximum, 24.1. And there's the line in between them. Now we're going to put one here for Q1. This is the median, and this is Q3. And now we're going to put a line above and below, and there's our box and whiskers. Now, here's what I need you to understand. Notice this is to scale, so 25% of the values are in this little area right here. Another 25% is in this little area here, in this range. And then 25% is in this range. And then finally, Q4, the largest of them all, has the same number of values. Notice that it doesn't make any difference how long this is. It just means that 25% of the values in this data set are in this particular spot. Well, this is much smaller than that, but they still have the same number of values. So there's like 3 values here and 3 values here. And then 3 and 3, or 4, 4, 4, and 4, something like that. Anyway, that's how you do that. All right, interpret the box part of your box and whisker spot. Okay, so for the box is this part right here. What can we say without a shadow of a doubt about this? Now we said 25% is here, 25% is here, 25% is here, and 25% is here. So if that's the case, then we can say that 50% of Mercury players fit inside this box because 25% is here and 25% is here. Averaged between 2.4 and 10.1 points. We know that that box has 50% of the players' points per game values. This 50% in the middle of the data is called the interquartile range, or IQR. If you've never heard of that before, that's okay. That's why we're teaching this. Statistics is a really, it's a brave new game if you've never done it before, but it's used all the time. I mean, in every avenue that you can think of when it comes to business or professional sports uses this all the time. You can see that we're talking about professional sports as the points per games of this particular WNBA team is being created into a box plot. All right, so you can create box plots on your calculator. Now what I'm going to do here is I'm going to use my calculator to do this. So I'm going to hit second y equals, and then I'm going to hit enter, and then I'm going to turn my data points on for plotting. See how it's blinking? Its cursor is on off. So right now my plots are off, but I'm going to hit enter and turn it on. Now you see that it's on, okay? Then I'm going to move the cursor to type, okay? So I'm going to move down, and I want to scroll right until I reach the box and whisker image. And that's this one right here. So I'm going to move it over until I get on that box and whisker image. So now I'm on it, I'm going to hit enter, and now the cursor stays on there. Then I'm going to go stat and enter, and then I'm going to enter the values that are in all of the data set. So I'm going to go back here and I'll look at my data value set, which is right here. And I'm going to put those values into L1. So I've got 24, let me get in here. 24.1, enter, and then I've got 21.2, 11.1, 10.1, 8.3, 5.8, 4.4, 4.1, 3.5, 2.7, 2.4. Let me go up there. I see that I'm missing a point. See that 35? That needs to be 3.5. And then 2.4, we go to 2.1, 1.8, and 0.8. So that's 15 values? No, it's 14 values. An even number of values. Remember, we had to split the middle two numbers. Now that I have this, I can go back to where I was, and I'm creating my box plot. Now I zoom 9 to graph only the information in the memory. Now I have all this in memory. If I hit the word zoom here, and I'm going to go to 9, I'm going to zoom to stat. Notice I put all the stat information into the stat column. So if I hit 9, it just pulls and puts in the values I need. Now it's not labeled, but it does look very similar to the one I built here. Okay? You can see this is somewhat stretched out, and I can change the window to make it look more like that if I wanted to. So for instance, I'm going to make the minimum 0. I'm going to make the maximum we said was, let's say 25. Minimum for Y is going to be 0. I don't really need to put a whole bunch in there because it's all in there. And now when I graph, it'll give you a better picture. Okay? So looks more like this. So as you can see, it's very easy to make a box and whisker, okay? So let's go back to the presentation and got all those done, and your image should look like that. As you can see, I've actually done that on the calculator. After the image is on the calculator, pushing the trace button allows the user to scroll to each of the 5 points on the 5-number summary, and the calculator will display both the value and which value represents the bottom of the screen. So let's look at that. Let's go to the calculator and hit trace. Notice it starts at the median at 4.25. And as you can see, we had calculated that. Q1 is 2.4, minimum is 0.8, Q3 is 10.1, and the maximum is 24.1. So everything we've done up to this point has been done correctly. So I think we did a good job on that. Let's continue on this lesson. There's an option in the calculator for creating a box plot that reveals outliers. Remember yesterday we talked about outliers, and these are values in the data set that are far outside the normal distribution. And you know it's outside of the normal distribution if most of the values are all like 1 or 2 points away from each other, and then the last value is like 10 points away from everything else. That's considered an outlier. So let's look at it. You do almost the same thing. You're going to do and look at the modified box and whisker image, then enter to selected. So it's exactly the same thing. We'll use the same values, but we'll just change the type of stat plot we use. And as you can see here, we're going to have to hit enter, and it's still on, but I'm going to scroll down, and this time I'm going to move instead of to the one that's highlighted there. This one has a couple dots on the outside of the box and whiskers because that's what's called outliers. They're outside the normal distribution. And now when I enter it and I hit graph, now I have this one dot that's way out here because it's an outlier. It lies outside, far outside of the normal distribution. Okay? And if we go back into the screen, as you can see, it should look something like that. Okay? Now, the school newspaper conducted a survey in which 31 randomly selected students were asked a variety of questions. Obviously, a new graphical display we're going to use. The responses to one question are shown in the following dot plot or line plot. Discuss what is known about these students. Okay, first of all, this is univariate data because these are actual values, and this is quantity of times they have. This is how many people, this is the number of hours of sleep the previous night these students had. One person had 3.5. 3 had 4.5, 4 had 5, 1 had 5.5, 8 had 6, 3 6.5, 4 7, 2 7.5, 2 8.5, or 2 8, 2 9, and 1 12. I don't know who this guy is with 12 hours of sleep, man, but he's obviously doing something right. So, some members of the newspaper staff wanted to report the sleep data in a frequency table as shown beside the screen. Discuss advantage and disadvantage of this option. So this is the number of hours of sleep, and this is the frequency. As you can see, it follows the same pattern as this last one. The only difference is it doesn't give every value in between. So if you have 4, 5, 6, 7, notice they don't have half values in here. So it looks a little bit different than this, okay? Other staff members voted for a box plot, which we've already discussed. Compare and contrast the usefulness of this box plot. Now, we said the disadvantage of this, it doesn't show the half values, and it may not look as accurate, this particular frequency table. And the box plot, it adequately describes, without a shadow of a doubt, what the 5-number summary is and where all the values are centered around, between 5 and 7, okay? But notice the box plot doesn't show that outlier out here. Now, other staffers argued the following graph with what were the reasons for preferring histogram. You can easily see where the normal distribution is depending on what you make your bin width as. If we made our bin width 3, we probably wouldn't see this as well. Against it, it doesn't necessarily give us all the information we want. We can't see every data point. And the dot plot, you can. You can see every data point. In this case, the X's show a data point. The real disadvantage of this, you have a very large data set. It's going to be very difficult to create this line plot or dot plot because there's so many values, it'll be hard to distinguish what's a dot and what's not. So How about this? The following dot plot shown the effect of separating data on male students' hours of sleep from the data of female students' hours of sleep. Now we've separated univariate data into two sets of separate data, but both univariate data. We're not showing a graphical display that discusses bivariate data, even though both of them together we consider as bivariate data. It's the same data, but for different categories. So this tells us really well the distribution of the values for either females or males. Notice that the females are all bunched between 4.5 and 8, and it looks fairly well symmetrical. But the males is between 3.5 and 12, and it's nowhere near symmetrical as the females. So that's actually pretty good if you're going to separate it. The following frequency table shows the effect of separating the data of male students' hours of sleep from the female students. This frequency table also does a good job of showing how the females' hours are bunched together and how the males are not. This Box-and-Whiskers shows the effect of separating the data on males and females students' hours of sleep. As you can see, this also adequately describes how the females are very bunched together. So we talked about something called, what was it called? The measure of spread outness, which is, I can't remember what it's called right now. Anyway, notice the females are not spread out. It's all bunched together between 5 and 8, or 4.5 and 8, but the males are spread out a lot. So these are the deviations, or the standard deviation. This has a smaller standard deviation. It's a large standard deviation. The larger the standard deviation, the more spread out the data values are from each other. And the closer they are together, the less spread out the data values are from each other. All right, now this is a histogram showing the separation. And this, as long as the bin widths are the same, you should be able to see pretty well the distribution is different, okay? Now, if they had different bin widths, you can easily convince someone that there's no difference because the bin widths are not the same, so the histograms might look similar. All right, so recall, and I'm going to launch you with this, recall that often when data is presented to the researcher after collection, they already have an idea of what they expect the data will reveal. And sometimes when I try a new method of teaching, though, I get surprise results from students doing much better than they expected. So understand there will be an assignment in the Google Classroom for this. Please get that done as soon as possible. It's due Monday. And in the meantime, please, I would like for y'all to be blessed and also be a blessing to the people around you.